Hello dear students, welcome to Physical Chemistry Classroom. Today we are going to discuss about phase equilibrium. This module includes phase rule, one component system, two component systems like Lead-Siller system, distribution law, partition coefficient and its applications. What do you mean by phase equilibrium? A phase equilibrium is a balance between phases, that is the coexistence of two or more phases in a state of dynamic equilibrium. Or phase equilibrium is a study of the equilibrium which exists between or within different states of matter, namely solid, liquid and gas. Phase equilibrium has wide range of applications in industries, including production of different allotropes of carbon, lowering of freezing point of water by dissolving salt, purification of components by distillation, usage of emulsions in food production, pharmaceutical industry, etc. These are the examples of phase equilibrium. First beaker contains only liquid water. Second beaker contains two phases, that is solid ice and liquid water. The third beaker, it contains liquid solid ice, liquid water and water vapor, gaseous water vapor. There are two types of mixtures, that is homogeneous mixture and heterogeneous mixture. Homogeneous mixture has the same uniform appearance throughout. That is homo. Homo means sameness. And the second one is heterogeneous mixture. A heterogeneous mixture consists of visibly different substances or different phases. Hetero means difference. The mixture of ice and water is an example of heterogeneous system. It contains two phases, one solid and one liquid. Mixture of gases, that is mixture of oxygen and nitrogen gas, has one phase which is gas phase. So it is a homogeneous system. Another example is oil-water system. It is a heterogeneous system. Decomposition of calcium carbonate is also a heterogeneous system. There are three phases: calcium carbonate phase, calcium oxide phase and carbon dioxide phase. Here calcium carbonate and calcium oxide are in solid phase and carbon dioxide in gaseous phase. Before going into the details of phase equilibrium, we can discuss some basic concepts in phase equilibrium. That is phase represented by the symbol P, component C, degrees of freedom F and phase rule. A phase is defined as any homogeneous, physically distinct part of the system which is mechanically separated from other parts of the system by definite bounding surfaces. A phase can exist either one of the state of matter, namely solid, liquid or gas. In general, gaseous system, only one phase is possible as gases are completely miscible with one another in all proportions. Another example, liquid system. The number of phases is equal to the number of layers present in the system. For completely miscible liquids, the number of phases is equal to 1. A system containing only one liquid water is one phase system. A system containing two liquid water and water vapor is a two-phase system. A system containing liquid water, water vapor and solid ice is a three-phase system. Next term is components. The number of components of a system is defined as the smallest number of independently variable constituents by means of which the composition of each phase can be represented by means of a chemical equation. Constituents can be either elements or compounds. If the composition of all the phases present in the system can be represented in terms of only one constituent, it becomes a one-component system. For example, water system. We know that water system consists of three phases: solid ice, liquid water, and gaseous water vapors. Each of the phases is nothing else but water. Hence, all the three phases can be represented in terms of the composition of only one constituent, that is by the formula H2O. So, water system is a one component system. Similarly, sulfur system has four phases: rhombic sulfur, monoclinic sulfur, liquid sulfur, and sulfur vapor. And the composition of all these phases is expressed by one chemical individual, sulfur. Yes. Therefore, sulfur system is one component system. Thus, all the phases in one component system is expressed by only one chemical individual. Another example is NaCl solution. A saturated solution of NaCl in contact with excess sodium chloride has two phases. The composition of both the phases can be expressed in terms of two chemical individuals, NaCl and H2O, water. Hence, a saturated solution of NaCl in water in contact with excess sodium chloride is a two-component system. Another example is decomposition of calcium carbonate. The case of dissociation of calcium carbonate is rather complicated. Consider the decomposition of calcium carbonate, that is, calcium carbonate solid gives calcium oxide solid and carbon dioxide gas. The composition of all the three phases can be expressed in terms of either of the two components. Any two out of the three substances can be chosen as the two components. Hence, or only two constituents are needed to express the composition of each of the three phases. Hence, it is a two-component system. That is, only two constituents are needed to express the composition of each of the three phases. Hence, it is a two-component system. Next term is degrees of freedom or variance, capital F. There are three variable factors, namely temperature, pressure, and concentration, on which the equilibrium of a system depends. In some cases, we have to mention only one factor to define the system completely, sometimes two or three. So, the degrees of freedom or variance of a system is defined as the minimum number of independent variables such as temperature, pressure, and concentration that must be ascertained so that a given system in equilibrium is completely defined. For example, in case of a pure gas obeying the gas equation, PV is equal to RT. If temperature and pressure are fixed, then its volume becomes automatically fixed. So only two variables need to be fixed in order to describe the system completely. So its degrees of freedom is 2, or the system can be said bivariant. Okay, considering the case of a system containing liquid water equilibrium with its vapor, only temperature need to be fixed to define the system, because the equilibrium vapor pressure can have only one value at a given temperature. In this case, the degree of freedom is 1, or the system is said to be univariant. Trivariant system. A mixture of two or more gases is completely defined only when pressure, temperature, and composition are specified. If pressure and temperature be specified, the third variable, that is composition, may be varied. Since it is necessary to specify three variables to define the system completely, it has three degrees. Thus, it is trivariant. That is, three variables means the system is trivariant. Two variables means the system is bivariant. One variable means the system is univariant. No variables, that means the system is invariant or non-variant system. Now consider the ice, water, water vapor equilibrium. Hence, no variable need to be fixed because all the three phases can remain in equilibrium only at a particular temperature and pressure. Hence, its degree of freedom is zero, or the system is said to be invariant. Thank you all for your patient listening.